The following program is brought to you by Caltech.
Hi, welcome back. Hope everybody had a good break. That first talk generated a lot of interest and conversation. But it's now my pleasure to introduce Dr. Shyam Menon, who's a postdoctoral researcher in the Mechanical Engineering Department here at Caltech. He completed his Bachelor of Science in Mechanical Engineering from VJTI in Mumbai, India in 2001. And after working for IT consulting for a year, he began his graduate studies at the University of Maryland at College Park in aerospace engineering. He completed his master's in 2005 and his PhD in 2010. His graduate work involved characterizing performance characteristics and energy losses in miniature internal combustion engines. He's currently working with Professor Guillaume Blanquois at Caltech doing numerical simulations of premixed flames with application to safety issues in aircraft fuel tanks. So please join me in welcoming Dr. Menon.
Thank you. Thanks for the introduction. Thank you for being here and coming to attend my talk. So my name is Shyam Menon, and I'm a postdoctoral researcher in the Mechanical Engineering Department. And I'll be talking to you today about some of the computational approaches that we use to model the use of natural gas in transportation applications. So before I move on to the talk, I'd just like to give you a little bit of my own personal research background. It's probably not as extensive as some of the other presenters here. But I completed my PhD towards the end of last year, and I was working on characterizing the performance of miniature internal combustion engines. So how miniature is miniature? I was looking at pretty much engines. The biggest engine that I was looking at was about that big. So really, this is miniature, and the smallest one was about that big. So we were looking at really small engines with applications to propulsions for UAVs and also for portable power systems. And so my task was to use experimental methods to characterize power efficiency, energy losses in these engines. Following which I've been working at Caltech for the past 9 months or so, and my work here has taken a pretty different, completely different approach, where instead of using experimental methods, I've been doing numerical simulation and using software tools to simulate laminar premixed flames with application to understanding hot surface ignition, where you could have a hot surface that is in contact with a flammable mixture, and you could have a possible explosion or flame propagation phenomena. So when I was initially asked to give this talk, I did make it clear that pretty much all the work that I've done in the past and what I'm doing right now deals with non-renewable energy resources. So primarily it's the combustion of hydrocarbons that I've been working on. But I did want to take this opportunity to try to see if I could use some of my knowledge in making a correlation between to try to understand how you could use or how natural gas is currently used in internal combustion engines, so as to solve some of the so as to reduce some of the dependence on petroleum use in internal combustion engines. So I wanted to try to make that connection and also try to see how some of the computational tools that I'm working on right now could help improve understanding of combustion of natural gas in internal combustion engines, which would help set a pathway for improved performance, improving the current performance of these engines, as well as come up with provide motivation for further improvement in performance of natural gas in internal combustion engines. So leading on from there, I'd just like to give you a brief outline of my talk. I'd also like to emphasize that much of this material has been collected, that I'll be presenting in this talk has been collected by reading through literature, scientific literature, and the internet and textbooks. A lot of the components of this talk will be sort of an overview in nature. So I apologize in advance if there's some of the material that I'll be covering is too basic in nature, but hopefully you'll still find it interesting. So I'll go over a brief outline of introduction and give you an introduction to natural gas and give an overview of natural gas resources around the world. Talk about some of the current global use of natural gas vehicles. I'll review some basics about internal combustion engines, talk about some of the major considerations that you come across when you're using natural gas in different kinds of internal combustion engines, including spark ignition engines and compression ignition engines. Then I'll talk a little bit about the computational modeling work, the current status of computational modeling work in internal combustion engines, and some of the advances in modeling just the combustion part of the cycle, which is what I'm more interested in doing, and which is what some of my current work is based upon. So we have some advanced methods of modeling the combustion process, which includes something called the flamelet approach, which I'll be talking about towards the end of the talk. And I'll just give an example of an application of this particular flamelet approach in modeling the performance of a natural gas engine, and finally present some conclusions. So just a brief introduction to natural gas. It is essentially a mixture of different gaseous hydrocarbons, with the primary constituent being methane, which is about 75 to 90% of the gas mixture. The composition varies widely, and it depends upon where the gas is extracted from, and also what kind of processing is done to the gas before it is supplied to the consumer. The typical composition is as shown in the table here. Most of it is comprised of methane, and then you also have other hydrocarbons, including ethane, propane, butane, some other elements, carbon dioxide, oxygen, nitrogen, and some trace amounts of rare gases. Now, just to give a brief, introduction, how is natural gas formed? Natural gas is a fossil fuel. You have different theories that exist as to the creation of natural gas. The majority of it is, of course, produced by the thermogenic process, where you have, which is illustrated in this figure here, where you have organic matter, which is basically animals and organic matter comprised of dead animals and plants, which is deposited on the Earth's surface. It gets buried under, it is covered by mud and sediments, and over millions of years, as it is subjected to high pressure and temperature below the Earth's surface, it results in the formation of petroleum as well as natural gas. Oil is found in shallower deposits because you have lower temperature there. It is created at shallower deposits because you have lower temperature there, while more natural gas is created at greater depths because you have higher temperature over there. Further, apart from the thermogenic process, you have biogenic methane, which is produced by microorganisms called methanogens, which break down the organic matter. And this is found to occur in areas of the Earth which are close to the surface, which are devoid of oxygen. It is also found in intestines of many animals. So the photograph here just shows some of the organic matter which can be broken down by methanogens and resulting in the formation of methane. Much of this is, of course, lost to the atmosphere, except for places like landfills, where you can actually extract the landfill gas, which is essentially natural gas, and can be processed and then supplied into the network, into the pipelines, which can finally take the natural gas to the consumers. Biogas to create landfill gas, you can use different kinds of biodegradable materials, such as biomass, manure, waste, plant material, and crops. One of the advantages of using of these landfill gases is that it reduces the emissions of nitrous oxide and methane, which would otherwise pollute the atmosphere and contribute to global warming and climate change. So this is the structure of a modern landfill, where you have essentially the trash, which is covered by a clay cap around it, and then you have an extraction system which allows the recovery of methane, which is formed by the organic breakdown, and it can be extracted from the landfill. The landfill gas formed in this manner can then be compressed and concentrated, and it can be injected into a natural gas grid and transported to customers. So around the world, if you look at biogas and landfill gas, you find that at least in the United States, only about 0.6% of natural gas is obtained in this manner. But in other places, for example, in the Indian subcontinent, it is widely used for powering individual farms and homes. In Europe, it is some amount of compressed biogas is also used to power vehicles for transportation purposes. You also have natural gas, which is found in the form of hydrates under sediment on offshore continental shelves, as well as on land in the Arctic regions. Currently, this kind of natural gas is very hard to extract, and the figure here basically shows the location of these hydrates in offshore continental shelves around the world. Once it is created in the Earth's crust because of the high temperature and pressure, because of its low density, it starts to rise towards the Earth's surface, and it is collected in trapped in geological formations under the ground in porous sedimentary rock. So as you can see in the figure here, you have oil and then a layer of natural gas which is collected above it, and it is the natural gas is trapped in these reservoirs underneath the Earth's crust, from where it can be extracted by your traditional drilling and extraction methods. So apart from the conventional reservoirs of natural gas which are formed as shown in this figure here, you also have unconventional sources of natural gas such as shale gas, which is this is actually the fastest growing natural gas resource in the United States and worldwide. It's essentially the same natural gas, but in this case it is still stuck in the original source rock instead of coming out and being collected in these reservoirs. Now, the technique that is popularly used to extract this kind of natural gas is called hydraulic fracturing, and you might have heard about it recently in the media, where it gets a lot of bad press because of the fact that people think the injection of chemicals and other substances during the course of this process results in contamination of groundwater, as well as might contribute to earthquakes. I don't want to touch upon that topic right now, but it suffice to say that the process itself consists of injecting water, sand, and other chemicals into the rock, as shown in this diagram over here, under pressure. And the result, what happens is that these materials create cracks or pores in the rock and allow the gas to be collected, the gas that is trapped in the rock to come out through the pores and then be extracted through these wells or pipes. Apart from shale gas, you also have methane, which is trapped in with coal deposits, as well as some which is trapped in sandstone. The chart over here shows the production of natural gas in the United States over the last 20 years, and also projected for some years into the future. What you can see here is that the production of conventional natural gas, which is shown in this color here, has tapered off a little bit and is expected to decrease over the coming years, while the production of shale gas is what is contributing to the major amount of natural gas that is extracted in the United States. So how do you find these resources of natural gas? So one of the earlier techniques was to basically conduct geological surveys, and the figure here essentially shows a time-lapsed movie created by the United States Geological Society, the USGS, of discovery of oil and gas in different locations in the United States over the course of many years. So the way these surveys are done is that geologists identify natural gas deposits by studying the surface structure, and additional information can also be obtained by looking at rock cuttings and soil samples. So you find that over the course of many years, the predictions of the amount of natural gas and oil that is present in the Earth's crust changes as new deposits are found, as well as sometimes you find deposits which could not be accessed earlier can now be accessed because of advances in technology. Apart from geological surveys, the more modern method of finding natural gas is using seismic exploration, which is essentially a process where you send seismic waves by different methods into the Earth's crust and study its interaction with the underground formations. So geophysicists produce artificial vibrations, which can be produced by different methods. One is using explosives, or it could be also by using special equipment like pistons, shown in this photograph over here, where you have a heavy piston which produces vibration in the rock, and the vibration, the information that is coming back and reflected from the Earth's crust is collected and processed by an instrument like a seismograph, which is essentially the same instrument that you use to track earthquakes. And then the results can show or reveal the presence or absence of natural gas and the quantity of natural gas. One of the sorry about that. Not now. Okay, Apart from, and one of the more recent advances in seismic exploration has been the use of computer-aided exploration, which allows geologists to study to use computer imaging in order to understand the underground formation in the Earth's crust. And this technique has allowed to considerably increase the accuracy in locating natural gas reserves. But one of the problems is that it generates a large amount of data, which then has to be processed. And currently, it's too expensive to be used for widespread use. Once a geologist identifies the location of natural gas, it is then you can then drill an exploratory well into the Earth's crust, and the geologists then examine drill cuttings and fluids in order to understand the composition of the underground rock, from which they can get more information regarding the kind of resources that are available, as well as the extent to which they are available in the Earth's crust. The next step is to extract the natural gas out of the reservoir, and this is done essentially by drilling through the Earth's crust. There are different methods that are followed here. The photograph here shows a rotary drill, which used to be the traditional way of drilling the well into the Earth's crust. In this case, you have the rotary drill bit digging into the Earth's crust and producing the initial well. And during the course of the drilling, you use fluids or air in order to remove the drill cuttings, as well as to cool the drill bit. A more recent advance is something called directional drilling, which has allowed a single well to access many different oil fields or natural gas fields. In this case, you drill vertically downwards, but then you use the hydraulic fracturing technique, which is used in extraction of shale gas, to drill horizontally along parallel to the Earth's crust, and this allows you to tap into the natural gas resources. Once it is extracted, it has to be processed, because the natural gas that is obtained from the Earth's crust is something that you refer to as wet natural gas. It has a lot of impurities, and it is also contains water. So you have to separate these components out, and this is done in a processing plant, where the major steps of processing the natural gas include removal of oil and condensates, removal of water, separation of natural gas liquids, and removal of sulfur and carbon dioxide. Natural gas has then to be stored or transported to the end user. The reason why it has to be stored is that, for one, at least in the United States, most of the use of natural gas is in residential heating purposes, and so there is only a seasonal demand for natural gas. So it has to be stored while it is not being used as much. And the other reason for storing natural gas is that in case of unforeseen circumstances where you can have disruption of supply of natural gas from other locations, you want to have a sufficient amount of backup to provide for your requirements. The storage facilities are typically in mines or depleted reservoirs or aquifers, which are essentially underground rivers, as well as salt caverns. The transportation of natural gas is accomplished by using a network of pipelines. These include interstate and intrastate pipelines. In order to transport the natural gas, it has to be first compressed, which is done by at compressor stations, where the gas is pressurized to between 200 to 1,500 pounds per square inch. This allows you to reduce the volume of the natural gas and also to propel it through the pipeline. Even along the course of the pipeline, you'll have pressure losses, and so you need compressor stations periodically along the pipeline in order to boost the pressure back up to its supply value. You have additional components of the transport system, but the photograph over here, or the figure here, essentially shows the pipeline coverage across the United States for natural gas, and you can see that much of it is centered in the areas where natural gas is produced, and then it is taken by pipelines to the different locations where it is consumed. So this figure just basically summarizes the natural gas production, transmission, and distribution system. It is produced at the oil or the gas well. You then separate out the oil and water from the natural gas. You have a processing plant which removes some of the other impurities. You have a compressor station which boosts up the pressure so that it can be transported through the pipeline, and then it is finally sent to the natural gas company, which can either store it or supply it to the end users. So just a brief history of natural gas. It has been observed to be escaping from the Earth's crust for a very long time in the past. There have been historical reports of lightning strikes which have resulted in ignition of natural gas leaking out from the ground. I found it interesting that the first use of natural gas was recorded by the Chinese, who used bamboo shoots to transport the gas and used it to boil seawater to make fresh water. One of the first commercialized use was in Britain in 1785 to light, and it was used to light street lights and lighthouses. In the United States, the first well was dug in about 1859, and natural gas, at least in the 19th century, was primarily used for lighting purposes. But this changed once with the invention of the Bunsen burner, which allowed you to basically burn the natural gas in order to provide energy for cooking purposes or for heating purposes. It is then the further use of natural gas is spread to industry in manufacturing and processing plants, and today the natural gas industry is about 100 years old and continues to grow rapidly. So just to go over briefly about the natural gas resources around the world. The natural gas, as you know, it's a non-renewable resource, and measuring the amount of natural gas reserves that are present today involves a great deal of inference and estimation. Globally, as you can see from this plot over here, much of the natural gas, similar to oil, is concentrated in the Middle East. The United States, in North America, has about 7.3% of global proven resources of natural gas, and of which 4% is in the United States. If you can also look at the reserves in terms of a ratio of reserves to production, which essentially works out to the number of years that you can expect the resource to last if you're consuming it at a certain rate today. So this figure shows the reserves to production in years for natural gas, and this one shows the same numbers for crude oil, and these are for different locations. I apologize for the fact that it's not very clear here, but it's essentially North America, South and Central America. It's hard to see from here, but Middle East, Africa, and Asia. But the thing to take away from this figure is that so the United States, North America has about, in terms of current production and consumption, you probably have around 20 years of natural gas left, while for crude oil, it is even lesser. It's about 15 years or so. But the thing to understand is that moving from one energy source to another, like from changing our fuel for transportation from crude oil to natural gas, would basically just lower this ratio down and deplete the natural gas resources at a faster rate. So at the end of the day, renewable energy is pretty much the only thing that can sustain us in the long run. But the message I'm trying to get across here is that since natural gas is more abundantly available in the United States, and more amounts of it are being discovered every year, it could serve as a bridge that could take us from our current situation with energy to a future situation where you're totally just dependent on renewable energy sources. So as I mentioned, in the amount of natural gas reserves in the United States, the prediction for the amount that is available goes up pretty much every year due to new discoveries of resources, as well as advances in technology that allow you to extract natural gas from resources that were formerly not accessible. So recently, because of the discoveries of shale gas and the extraction of shale gas, you can see that there has been an increase in the proven reserves for natural gas. That is a good question. I mean, I would think that's probably the reason, that it's lesser than what was initially expected, and they have changed their expectations of the amount of natural gas that's available offshore.
It could be because of the way reserves are calculated. They don't count as reserves unless they're economic. When you go to a reserves company to have your reserves evaluated, they won't count it if it's non-economic. So as the price goes up to develop those, reserves drop off the table.
So it's not the absolute amount of natural gas, it's actually what is economically feasible to extract out from the Earth's crust.
So I have a question. Back in the previous chart, there was only 15 years or something of natural gas in North America, and did that include all the shale gas discoveries?
did this include, so the question is if this graph includes the amount of shale gas that has been more recently discovered in the United States. I think the answer to that is no. This is taken from the British Petroleum's comes out with an annual review of the energy sources around the world, and from what I can remember, it was pretty much just the conventional natural gas resources and not that which can be extracted from shale gas. So I don't think it's reflected in this graph. In terms of global natural gas consumption, again, this is a figure taken from British Petroleum's data. This chart shows the consumption of natural gas by region in terms of for the rest of the world. Well, for the United States, for North America, for Europe, for Asia Pacific, and for the rest of the world over a number of years. And what you see is that in North America, the amount of natural gas consumed has not changed significantly over time, while in recent years in Asia Pacific, this has started to increase considerably because of the more and more use of natural gas in transportation industry as well as in other applications. Regulation of natural gas, I just wanted to briefly mention that natural gas is currently much less regulated than in the past, and there are different levels of regulation. Producers and marketers are not directly regulated. However, transmission and distribution providers are regulated, and this is done to make sure that no single producer of natural gas can dominate the market by offering, an unfair. None of these producers can get an unfair advantage over the other producer of natural gas in terms of getting their product out to the consumer. And currently, this is done by the Federal Energy Regulatory Commission. If you look at the price of natural gas, again, you have prices which are for natural gas in the United States, the German import of price of natural gas in the United Kingdom and Japan. You find that pretty much all of them tend to correlate with each other, and the price of natural gas, which actually used to be kind of dormant for a long amount of time, has started to increase in the recent years. And I think, at least in the last few years, because of the downturn in the economy, the price of natural gas has come down a little bit, but it is now starting to pick up again. But something interesting to note is that the cost of natural gas can be as low as $0.64 for an equal gallon of gasoline. So there can be considerable amount of savings that can be accrued in fuel costs by switching over from gasoline to natural gas. So I'll briefly try to go over some of the physical properties of natural gas as well as some of the emission characteristics. So the table here lists some of the important physical properties of natural gas. Since it is mostly composed of methane, you have the chemical formula CH4. As compared to gasoline and diesel, it is a much less lighter hydrocarbon and also has much fewer carbon atoms. This bodes well for emissions in that you're going to have lower amount of CO2 and carbon monoxide produced as a result of combustion of natural gas. If you look at density, since it is in the gaseous form, the density is low. It's about 0.8 kilogram per meter cube as compared to 750 or 835 for gasoline and diesel. So this reflects in the heating value of the fuel. So if you look at the heating value per unit mass, which is megajoule per kilogram, you find that the heating value of natural gas is comparable or better than that for gasoline and diesel. But if you could take it as per unit volume in terms of megajoule per liter, which is important when you're considering the storage and transportation of the fuel, you find that the heating value gets considerably reduced because of your low density for the fuel. So this means that the gas has to be compressed or liquefied in order to use it in transportation purposes, so that you can have enough range for your vehicle to travel on the fuel. If you look at the auto ignition temperature, you find that natural gas is actually safer than gasoline or diesel, having a higher auto ignition temperature. The peak flame temperature is about the same order as that of gasoline and diesel. Something important to note, and that I'll touch upon later in one of the slides down the line, is that the stoichiometric air-fuel ratio is actually higher than that for gasoline and diesel. So for those of you who are not familiar with this term, it tells you the quality of the fuel-air mixture. So if you if you say that if you're operating at a stoichiometric fuel-air mixture ratio, which is the ratio of the mass of fuel to the mass of air, it means that you have exactly the right amount of oxygen that will convert all the carbon in the fuel to carbon dioxide and all the hydrogen in the fuel to water. If you go, if you're operating rich, it means that your equivalence ratio is greater than 1. It means that you have more fuel and less air. If you're operating lean, it means that you have more air and less fuel. Now, as I mentioned before, because the natural gas has fewer carbon atoms, you find that the emission of carbon dioxide per gram of fuel is actually lower for natural gas as compared to gasoline and hydrogen. This chart pretty much reflects something that I presented in the table in the previous slide. We're looking at energy density in terms of energy per unit mass, which is megajoule per kilogram, and energy per unit volume, which is megajoule per liter for different fuels, including, so if you look at this graph, we have diesel, which has about 42.5 megajoule per kilogram, gasoline, which is 44. Hydrogen is a fuel which has the highest amount of energy content per unit mass, which is about 120 megajoule per kilogram. And natural gas clocks in at about 50 megajoule per kilogram, and this is at standard temperature and pressure. But now, in terms of looking at storage requirements, if you look at the enthalpy of combustion, or the essentially the heating value in terms of megajoule per liter, you find that although diesel and gasoline still have energy densities in the 36 and 32 megajoule per liter, for hydrogen it goes down all the way to 0.01 megajoule per liter, and for natural gas it goes down to about 0.04 megajoule per liter. But by compressing the gas, you can increase the energy content, and also by liquefaction, you can achieve energy densities as high as 21 megajoule per liter. So the majority of the vehicles that do operate on natural gas operate on compressed natural gas, CNG. It is stored in tube-shaped cylinders, which are attached to in different parts of the vehicle. They operate. The tanks are kept in a high pressure, between 3,000 to 6,000 pounds per square inch. These tanks are designed in order to meet very high safety standards, and they're made to withstand puncture and impact, and they're capable of venting gas in the case of a fire. They can also be stored as liquefied natural gas by cooling them down to a very low temperature of minus 260 degrees Fahrenheit. The advantage of this is that the liquefied natural gas occupies about 30% less space as compared to CNG for the same energy content. But the drawback is, of course, you have to keep it cool, and so you have to store it in a thermal storage tank. Finally, since natural gas is in the gaseous form, you need a special sort of receptacle in your fuel tank, as well as a nozzle in the refueling stations, in order to maintain a leak-free seal between the supply and the fuel tank. There are also companies that sell essentially a miniature fueling station, which you can install in your garage, and it essentially comprises of a small compressor which takes the natural gas from the supply network and compresses enough so that you can actually inject it into the fuel tank in the engine. If you briefly look at emissions from internal combustion engines, the primary emissions, of course, are carbon dioxide, water, nitrous oxides, unburned hydrocarbons, including particulate matter like soot, and then you also have sulfur oxides. Now, the creation of how much of these kinds of emissions are produced in the exhaust and depends upon two important factors. One is the equivalence ratio, and the other is temperature inside the engine. So the plot here essentially shows emissions of nitrous oxide, hydrocarbons, and carbon monoxide as a function of equivalence ratio. So as I said before, equivalence ratio gives you a feel for the mixture quality inside the engine. So when you're operating at equivalence ratio 1, it means that you have exactly the right amount of air to convert carbon to carbon dioxide and hydrogen to water. So that's where you're going to get your peak temperature, because that's where when you're operating at equivalence ratio 1, you're releasing most of the energy in the fuel and changing it from chemical energy to thermal energy. As you go towards rich mixtures or lean mixtures, the temperature goes down, and you also change the combustion behavior. So most of the carbon, as you move towards a rich mixture, because there's more carbon in the fuel and there's less oxygen to oxidize the carbon, you end up creating more hydrocarbons, particulate matter, as well as more carbon monoxide. This decreases as you go towards lean mixtures. The formation of nitrous oxide is essentially related to the temperature inside the cylinder. So since nitrous oxide is formed by a thermal mechanism, the maximum amount of nitrous oxide is formed when the temperature inside the cylinder is the highest, which happens at equivalence ratio of 1. Since the temperature falls down on either side, you find that the amount of nitrous oxide produced also decreases. As I mentioned before, natural gas benefits from having a lower carbon content, and that will produce lower amount of CO and hydrocarbon emissions as compared to gasoline or diesel. Now, when you're looking at emissions from different fuels, there's another consideration that you have to keep in mind, is that the emissions can come not just from the engine in which you're burning the fuel, but also from the extraction and processing of the fuel itself when you're taking it from the well to the pumps. So the right way to do this analysis is by computing the total amount of emissions when you take the fuel from the well and then you burn it in the engine and produce energy to power the wheels. So this is sort of analysis that is shown in this schematic here, where this wheel-to-well analysis has been done to estimate the amount of emissions for different types of vehicles, including gasoline vehicles, vehicles running on ethanol-based fuels, natural gas vehicles, hybrids, and so on. So one of the things that you'll notice here is that natural gas vehicles perform, if not equal, perform definitely better than gasoline vehicles, and about the same, produce about the same amount of emissions as an ethanol-based vehicle. I also have in this chart over here some results from field tests done on natural gas vehicle emissions by the Department of Energy, which tried to monitor the amount of emissions from vehicles which are converted from diesel to operate on natural gas, and which are used in different fleet applications such as delivery trucks, LNG buses, refuse trucks, and etc. So what they found that across the board, you could obtain a reduction in the emissions for particulate matter, NOx, and carbon monoxide by switching over from diesel to natural gas. There were a couple of cases where you saw an increase in the amount of carbon monoxide content in heavy duty trucks which operate at high loads, and this is something I'll be discussing in one of the future slides. But for most parts, you can achieve a pretty good reduction in emissions by switching over from diesel to natural gas based fuel. So I just want to briefly discuss the role of natural gas in the current energy supply scenario. So this is a figure you might have seen before, which was developed by the Lawrence Livermore National Lab to show the estimated energy use in 2008. So you have all the different sources of energy here, including renewable energy resources, including solar, nuclear, wind, geothermal, etc. And then you have natural gas, the non-renewable energy resources, natural gas, coal, and then you also have petroleum down here. So, and then these energy sources are then traced to where they're finally applied, such as in electricity generation, you have residential applications, commercial applications, industrial, and transportation. So what I'm more interested in is the transportation application. So you can see that the majority of the energy comes from, obviously, from gas, petroleum sources. The amount that is current, at least in 2008 standards, the amount of energy that came from natural gas was very small as compared to what came from petroleum. So this is again reflected in this chart that I have on this slide, which basically shows the amount of energy, the energy breakup as in the okay, so what this chart essentially shows is where the natural gas that is extracted is finally utilized. So you have, if you look at vehicle fuel, you see that about less than 1% of the natural gas that is extracted is used as vehicle fuel. while if you look at in terms of the amount of natural gas that this comprises in terms of the total fuel that is used in transportation, you find that only about 2% of the fuel that is used in transportation comes from natural gas. So it's a very small content, at least in the United States. So I also wanted to look at, in this chart, what are the types of vehicles in which you finally consume the gasoline that is used in the transportation sector. You find that the majority of the gasoline is used for personal transport in cars, pickups, and SUVs. So the amount of gasoline that is actually used in mass transportation as well as air and rail transport is smaller than than the amount of gasoline that is used for personal transportation vehicles. Just to go over the current use of natural gas vehicles in the transportation industry, we saw that not much of natural gas is used in vehicular transport in the United States, but worldwide it's not the same case. You actually find, and so in this plot you have the number of natural gas vehicles by region for Asia Pacific, Europe, North and South America, and Africa over the course of a number of years. You find that in recent years, at least in the last decade or so, there's been a very rapid growth in the number of natural gas vehicles in the Asia Pacific region, as well as in South America and to some extent in Europe. While in North America, the number of natural gas vehicles are still lagging behind as compared to the rest of the world. And going by current trends, it is estimated that you can almost have an exponential growth of natural gas vehicles worldwide, at least for the next couple of decades or so. Now, along with the natural gas vehicles, you also need the infrastructure to keep pace with the increase in the number of natural gas vehicles so that you can supply the fuel to the vehicles. So what this chart over here shows is the number of refueling stations which were established worldwide over the last few years in different locations. So you find that in the United States, the number of there's been only a very slow growth in the number of natural gas vehicle refueling stations, and as compared to the rest of the world. But there are still about 1,000 refueling stations, with the highest number here in California. And the number of natural gas vehicles currently in the United States are about 115,000, but it is still very small as compared to the number of vehicles that burn conventional fuel, which is numbers in the hundreds of millions. Natural gas vehicles are very amenable to be used in fleet transport, and this is because and examples of fleet transport include vehicles which are used by local, state, and federal government, or vehicles which are used near airports, vehicles used in collecting garbage and refuse, vehicles that are used for mass transit, as well as short haul distribution and delivery, as well as for commercial services. Now, the reason why natural gas vehicles are so useful in fleet transport is that you have a centralized location of the natural gas refueling station, so that it can supply fuel to all the vehicles in the fleet. The fleet vehicles generally accrue a large number of miles, so you can have a considerable reduction in savings in fuel costs by switching over from conventional fuels to natural gas-based fuel. The maintenance costs for natural gas vehicles are found to be lower or equal to that for diesel or gasoline. You also have advantages with getting federal tax credits, which reduce your initial investment costs of conversion from traditional fuels to natural gas. And at the end of the day, you also get quieter vehicles, which make less noise than comparable diesel engines. So just to briefly go over some of the future prospects of natural gas use in transportation. There's some industry data which has showed that vehicular natural gas use has almost doubled in the last decade or so. A lot of this growth has come from mass transit buses, which account for about 62% of all vehicular natural gas use. The waste collection and transfer vehicles are actually the fastest growing segment in natural gas vehicles, and it is estimated that in the next 10 years or so, about 9% of worldwide transportation fleets will be switching over from conventional fuels to natural gas. So now I'd just like to go over some of the major considerations that arise when you convert when you either convert your operation of internal combustion engines from conventional fuels like gasoline or diesel to natural gas, or when you're developing a new engine altogether to operate on natural gas. So just to give you a brief introduction, of course, an internal combustion engine, it's a device where you have combustion of fuel and air inside the combustion chamber to produce motive power. It is the most widely used portable device for portable power applications, mainly because of its high power to weight ratio. It has many different uses, majority of which are in transportation and power generation. These engines operate in different cycles and configurations. The main configurations in which they are used in the transportation field are reciprocating engines, which could comprise of spark ignition gasoline engines or compression ignition diesel engines. And apart from this, you have rotary engines, the gas turbines used in air transport. So the primary application of natural gas is in transportation through reciprocating engines, which can be used in automobiles, trucks, trains, ships, etc. So the combustion in reciprocating engines occurs in two different modes, as I mentioned in the previous slides. It depends upon the fuel that is used. And so if you're using gasoline, you operate in a spark ignition mode, and it operates on the thermodynamic cycle called the Otto cycle. If you're using diesel, you operate in the compression ignition mode, and it follows the diesel cycle. So the major difference between the two cycles arises from the nature of the fuel use and the combustion process itself. If you're operating in the spark ignition engine, you have combustion which occurs through a flame propagation phenomena. So you have a laminar or turbulent flame which is propagating through the combustion chamber and converting the reactants to products and releasing chemical energy in the form of thermal energy. In the case of a diesel cycle, instead of having a single laminar flame propagating through the combustion chamber, what you actually have is a mixing controlled diffusion and burning process. So you have a fuel which is injected into the combustion chamber in the form of droplets, which vaporizes in the high temperature region inside the combustion chamber, and then you have a droplet burning phenomena which actually releases the chemical energy, the fuel, in the form of thermal energy. So to briefly illustrate the working of the SI engine cycle, it must be from like high school textbooks. You might have seen the operation of the SI engine cycle, but the figure here shows an animation of the cycle. The different positions of the piston inside the cylinder are illustrated over here, and what I have on these graphs are essentially the pressure volume, the PV diagram, and temperature entropy, or the TS diagram. So these are the diagrams which allow you to track the thermodynamic property of the mixture inside the cycle during the inside the cylinder during the course of the cycle. So you have at some point you have intake of fresh gas through the intake valve, and that is the intake process, which is actually not shown over here. But then you have compression as the piston moves upwards, and so this is the compression process. At some point you have ignition and combustion, which results in the release of energy, and then you have the expansion process in which the thermal energy is converted into mechanical work, and finally you have a heat rejection process in which the burned gases are pushed out of the exhaust port. So if you integrate the area inside the curve, you essentially end up getting the work output from the cycle, and that can be then converted into power if you know the number of revolutions you have per minute. Now, it is possible to do a simple thermodynamic analysis to calculate the efficiency of the Otto cycle. And so what you essentially do is that you go through these different processes, which are isentropic compression, and you assume that they're idealized. So you have an ideal compression with no heat losses. Then you have constant volume heat addition, isentropic expansion, and constant volume heat rejection. And by just analyzing these processes, you can come up with a expression that gives you the theoretical efficiency of the cycle. And so that is shown in this equation over here. So you have that the efficiency of the Otto cycle is given as 1 minus 1 over compression ratio raised to gamma minus 1, where CR is the compression ratio. So the compression ratio is essentially the ratio of the volume before the start of the compression to the volume at the end of compression. So you can see from this expression that any increase in the compression ratio will allow you to increase the theoretical efficiency of the cycle. So that is shown in the graph here, where as you increase the compression ratio, you increase the thermodynamic efficiency of the cycle. But then there are limitations that are imposed by the fuel on the amount of compression, on the compression ratio that you can have in the engine. So for gasoline, the typical compression ratios lie in this range, and so you end up with theoretical efficiencies of between 50 to 60%. And again, these are based on idealized calculation. So when you take into account real gas effects, heat transfer, frictional losses, and so on and so forth, the final efficiency that you get is even less, is much less than the 60% that you can get from this analysis. But it is important to note that how compression ratio is linked to the thermodynamic efficiency of the cycle. In the case of a diesel engine, you still have the same compression compression, expansion, intake, and exhaust process. The major difference arises from the way in which the combustion process takes place. In the case of the spark ignition cycle, we saw that the compression, which was illustrated by the process going from 2 to 3, happened at constant volume. It was a straight line. Vertical line. And so in this case, the combustion happens at constant pressure instead of constant volume. So that is a major difference between the SI engine cycle and the CI engines and the compression ignition engine cycle. Apart from that, the processes are pretty similar, except that, of course, in the diesel cycle, you do not have a spark ignition. The ignition happens, and the fuel-air mixture auto-ignites because of the high temperature and pressure at the end of the compression process. Similar to the SI engine cycle, you can derive an expression for the thermodynamic efficiency of the diesel cycle. So you end up with an expression which looks a little bit similar to the previous one, except that you have this additional term in the bracket over here. And that arises from, what you have here, this parameter RC represents something called the cutoff ratio. So that is the ratio of the volume at the end of the heat addition process or the combustion process to the volume before at the start of the combustion process. So you end up having that additional parameter in here. But other than that, you can still plot theoretical efficiencies of the diesel cycle as a function of compression ratio. Now, with diesel, you can have a higher compression ratio, which means that you can have higher efficiencies. Now, for the same compression ratio, you actually get a lower theoretical efficiency for diesel as compared to the spark ignition cycle, but the fact that you can go to higher compression ratios allows you to have an improved thermodynamic efficiency. When you're thinking about designing an engine for natural gas use or converting an existing spark ignition or compression ignition engine, there are basically 3 different approaches. One is to retrofit the existing engine by using a conversion kit, which are available in the market. Another approach is to use a dual fuel in the engine, where you could be using both natural gas as well as conventional fuel at the same, well, not at the same time, but you're switching over from one fuel source to another. And finally, you could basically start from scratch and design a completely new engine for exclusive use with natural gas. So we'll now look at, before we look at some of the issues of converting existing spark ignition or compression ignition engine to use with natural gas, I'd just like to show you an expression which basically expresses the power output of the engine in terms of the main parameters that control the power output from the engine. So you have, in this expression, you have the W dot B actual, which basically represents the actual amount of power output from the cycle, and it is given as a product of several different parameters. You have K, which relates to the type or the configuration of the engine, if it is 2-stroke or 4-stroke. So it is equals 1 for 2-stroke because you're releasing, you have 1 power stroke per revolution of the crankshaft, while it is half for 4 strokes because you have 1 power stroke per 2 revolutions of the crankshaft. Then you have the thermodynamic efficiency, which basically tells you how efficiently you're releasing the chemical energy of the fuel and converting that into thermal energy during the combustion process. You have the volumetric efficiency, the eta V term, which basically tells you how well you're ingesting air into the engine. So you can think of the engine as an air pump, in that it's essentially taking air from the outside and putting it inside the cylinder. So there's an efficiency factor that's associated with it, and that is called the volumetric efficiency. You have the density of the air, the intake. You have VD, which is the displacement volume, which is the size of the engine, essentially. You have the engine operating speed, which is expressed through NS. You have the equivalence ratio, which I mentioned before, and is expressed as the ratio of the fuel air, actual fuel air mixture ratio that's burnt inside the engine to the stoichiometric value. That also enters into the expression for power output. And finally, you also have the heating value of the fuel. So you can see that to increase the amount of power output from the engine, since it is directly proportional to all these factors, you can achieve it by increasing the thermodynamic efficiency, increasing volumetric efficiency, increasing the density at the intake, increasing the size of the engine by increasing the displacement volume, increasing the speed of the engine by increasing operating speed, or by using a fuel with a higher heating value. So in terms of using natural gas in spark ignition engines, spark ignition engines can be easily converted to run on natural gas. The main considerations to keep in mind while you're doing this conversion are 4 different things, which we'll be talking about in the following slides. One is fuel delivery, one is compression ratio, one is flame speed, which is the speed at which you consume the reactants, and that's related to the combustion efficiency, and finally also the ignition or the spark timing. Commercially, so this photograph here shows basically what's under the hood for the only vehicle that runs on natural gas that is commercially available in the United States, which is made by Honda. The other figure over on the right shows basically the location of the fuel tank, and that's one of the drawbacks for using natural gas vehicles, in that you're going to lose out on trunk space because it is occupied by a large compressed natural gas cylinder, which serves as the fuel source. So, as I mentioned, one of the major considerations in switching over from natural gas to from gasoline to natural gas in spark ignition engines is the fuel delivery. So there are 2 methods in which fuel is delivered into the natural gas is delivered into the spark ignition engine. The popular one is port injection, which is and it's popular because it's cheaper and an easier method of introducing the fuel. So what you essentially do is that you have natural gas that comes from the tank sitting in the trunk of your car, and it is injected using high pressure injectors, which are shown over here, directly into the intake manifold, and that's going into the cylinder head of the engine. So this is the intake manifold that carries air into the engine, and you directly inject the natural gas into the intake ports. Now, one of the issues with doing this sort of fuel injection is that you end up losing out on volumetric efficiency of the engine, and as we saw in a couple of slides before, power output was directly proportional to volumetric efficiency. So any drop in volumetric efficiency means drop in power output and drop in overall efficiency of the engine. Now, the reason why you drop and lose volumetric efficiency is that since natural gas is in the gaseous form, when you inject it into the intake port, it displaces some amount of air that would otherwise have gone inside the engine. So the engine is actually receiving a smaller amount of air than it ideally expects. So you're losing out on some, so there's a drop in volumetric efficiency. Now, there's a way to compensate for this, and that is by increasing the density of the air that's coming in through the intake manifold by using turbochargers or superchargers. But then this brings additional complexity into the engine design. The other method of fuel delivery, which can actually reduce some of the losses in volumetric efficiency that occurs due to port injection, is by using direct injection. So in the case of direct injection, instead of injecting into the intake port as you would normally do in the port injection method, you actually directly inject into the combustion chamber. So in this case, you avoid the losses in volumetric efficiency, but the problem with this case is that you need special high-pressure injectors which are capable of injecting into the combustion chamber, which operates under high pressure. And these are expensive, and that makes it prohibitive right now. And the other drawback also is that you need to if you're retrofitting an existing spark ignition engine to operate on natural gas, you need to do modifications in order to allow this high pressure injector to access the combustion chamber volume. So that adds to the complexity and the cost of conversion from gasoline to natural gas. One of the methods that some researchers have come up with of avoiding this problem of modifying the cylinder head is to inject the natural gas along a small pipe that is actually closely coupled with a spark plug. So this allows you to inject natural gas into the engine without having to do any major modifications. This still requires a high pressure injector, but it's just that you're reducing some of the labor costs in installing the natural gas kit into your engine. The second issue, a major consideration for using natural gas in spark ignition engine is the compression ratio. Now, octane number is something that qualifies the the combustion quality of the fuel. So the higher the octane number, you find that you can increase the compression ratio inside the engine without causing serious harm, which would occur. Traditionally, the way you want combustion to happen in a spark ignition engine is by the propagation of a flame. But if you increase the compression ratio, too much, what you end up having is that instead of a flame propagation, you can have a detonation phenomena, which will cause severe engine damage. So the octane number is what tells you how high the compression ratio can go without risk of damage to the engine. So what you find is that the octane number for natural gas is higher than the octane number for gasoline, and this allows you to have a higher compression ratio inside the engine. And we saw before from the expression for the theoretical efficiency that the higher the compression ratio, you can have higher overall efficiencies. So these plots are not very clear at all, but it basically shows the power output from the engine plotted on the y-axis as a function of, I think, something I'll talk about in the next slide, exhaust gas recirculation on the x-axis. But the important thing to note here is that three different data sets have been plotted here with different compression ratios. And what they have found is that with the increasing compression ratio, you can have increasing amount of power output from the engine without changing any other operating parameters. Along with the improvement in power output of the engine, you also get an improvement in efficiency, which is what is supposed to be seen on the graph on the right hand side, where what you have on the y-axis here is the brake specific fuel consumption. So it tells you the amount of fuel consumed per unit power produced. So it's an inverse of efficiency, and it basically means that increasing compression ratio lowers the BSFC, which means you get improvement in efficiency, in overall efficiency. So another consideration for use of natural gas is the flame speed, which is related to the combustion efficiency. So we find that the flame speed for natural gas is actually lower than that for gasoline and diesel. Now this is a concern because the flame speed actually tells you how quickly you can burn the mixture inside the engine. And you want, in an internal combustion engine, which is operating traditionally at high speeds, there's only a limited amount of time that is available to burn all the fuel before you open up the exhaust valve. So if your flame speed is lower, it means that not all the fuel can be consumed, which means that there'll be a loss in overall efficiency, as well as you also have increased emissions of unburned hydrocarbon fuels. So the solution here, to fix the problem with the low flame speed, is that you add a secondary fuel such as hydrogen, which has a much higher flame speed than natural gas, and this allows the whole mixture as a whole to have a higher flame speed, and so that you do not lose any combustion efficiency and do not produce excessive emissions. Another method of increasing the flame speed is by producing in-cylinder turbulence. Turbulence is essentially producing disturbances in the fluid inside the engine, which allows the flame speed to be increased. So you can artificially generate turbulence by creating certain structures inside the cylinder volume. So what I'm showing in these figures here is that over here you see that the flame speed for the mixture of natural gas and hydrogen goes up as you increase the hydrogen content in the fuel from 0 to, say, 100%. There's a considerable increase in the flame speed. This increase in flame speed can be obtained at all different equivalence ratios. So here, what you have is flame speed plot as a function of equivalence ratios for different mixtures of hydrogen and natural gas. For 0% of hydrogen in the mixture, you find that there's a certain distribution of flame speed, but the flame speed at all the equivalence ratios goes up as you increase the amount of hydrogen gas content. Finally, what this figure shows here is a way of generating turbulence inside the engine by producing something called a squish volume. So in a traditional engine where you would have these surfaces flat, you put a little bit of a triangular indentation inside the cylinder volume, and which results in the formation of recirculation regions and allows you to create turbulence, which can increase the mixing and increase the flame speed and reduce the flame travel time. Ignition timing is another parameter that comes into effect because And again, this is an effect which is similar to that of burning speed. The fact that natural gas has lower burning speed means that you need to ignite earlier in the cycle so that you can complete the combustion of all the fuel. But igniting too early in the cycle is problematic because if you think about it, if you ignite at the mixture at the point where the piston is moving upwards, what you end up doing is that you're producing high pressure inside the cylinder as the piston is moving upwards. So you're actually producing negative work. So you're actually losing out on the work output from the cycle because you're essentially working against that high pressure generated by the combustion process. So the solution to this is that basically you have to carefully balance the spark timing and the injection timing so that you can get the optimum engine performance from your when you convert the engine to operate from gasoline to natural gas. And so the main thing here is tuning of the engine once you have all the other components in place. So you have aftermarket kits that are available to do these sort of modifications. They have a large number of components, and I have a photograph of one of such kits which is available in the market, just so you can see what it involves. The costs for these conversions are still considerable, especially if you consider them for personal use. They range from between $12,500 to $20,500, and the main cost of the majority of these costs actually go into the tank itself, as well as the labor involved in doing the conversion. So although if it is not currently at the higher end for most consumers, it can be still justifiable for fleet consumers who end up saving a lot of costs for fuel consumption because of the large number of miles that they accrue on their vehicles. In addition to this, you also have tax credits and rebates that can give you more incentive to convert from gasoline to natural gas. The refueling kit that I showed a photograph of before costs about $4,000 by itself, and generally it is not very advisable to convert an older vehicle to natural gas. If you look at the performance of an engine which has been converted from gasoline to operate on natural gas, you find that, first of all, the power output tends to go down. And this is because of one of the reasons that I mentioned before, that the volumetric efficiency of a converted engine goes down because of the fact that you're not getting enough air into the engine. So the figure here shows the power output plotted for an engine which is not being turbocharged or supercharged as a function of vehicle speed, and you find that the power output from the engine goes down as you convert the engine to operate from gasoline to natural gas. One of the benefits of using natural gas, though, is that you can operate at lean mixture ratios, which are essentially equivalence ratios much less than 1. Typically, operation in this regime allows you to have better fuel economy as well as to reduce emissions. But this is not operation in this mixture is not possible with gasoline because it results in excessive cycle-to-cycle variation. So the plot over here shows is on the y-axis you have something called the coefficient of variation, which basically signifies the level of cycle-to-cycle variation during engine operation, and on the x-axis you have equivalence ratio. So for gasoline, there's a limit to which you can operate in the lean regime, but with natural gas, you find that the coefficient of variation is still low as you go to very lean operating mixtures, and you can operate on natural gas in these regimes and achieve some fuel economy and reduction in emissions. Apart from operation lean regimes, one of the issues with using natural gas in a spark ignition engine is that you end up forming a lot of NOx, and this is because of the high temperature and pressure inside the combustion chamber when you switch from gasoline to natural gas. So one of the techniques that is commonly used to reduce the formation of nitrous oxides is something called exhaust gas recirculation. So what that basically involves is taking the exhaust gas from out of the exhaust manifold and recirculating it in the cooled or uncooled form, and basically injecting it back into the engine combustion chamber. So what this essentially does is that it reduces the peak temperature inside the engine and reduces the formation of NOx. Now the drawback to this is that the more amount of exhaust gas you pump back into the engine, you end up reducing your flame speed further. So this causes an issue with having good combustion efficiency and reduction and if you have a low flame speed, you have poor combustion efficiency, and you have excessive emissions of unburned hydrocarbons. So if you are using EGR, then it means that you have to go back and add hydrogen into the engine so that you can get your flame speed back up so that you don't lose out on the combustion efficiency. So there are trade-offs associated with these different strategies, which have to be followed in order to maximize the performance of your engine. The graph here essentially shows the efficiency of the engine, and what you have on the x-axis is spark timing. So let's just follow curve 1 here, which essentially is for an engine which is operating with no hydrogen and no exhaust gas recirculation. So this is your baseline configuration. When you move to curve 2, where you have about 15% by volume addition of hydrogen, you find that there's an improvement in performance, and you get an increase in efficiency, primarily because of the increase in flame speed. Now, because your temperatures are high here, you're still forming a lot of NOx. So what you have to do now is you have to use exhaust gas recirculation in order to reduce the NOx by lowering the temperature. So now the problem is that because you're injecting, so if you follow curve 3 or 4, it's basically this case for modified from curve 1, where you still don't have any hydrogen, but you have exhaust gas recirculation. Now, because you have exhaust gas recirculation, your flame speed decreases, so you have to ignite earlier in the cycle. So you're basically pushing your spark timing earlier and earlier into the cycle. This results in loss of efficiency. Now, to get back to your original efficiency, your improved efficiency that you got from addition of hydrogen, you have to add hydrogen to the EGR case as well, and that can boost up your efficiency to these levels. So I just wanted to illustrate all these different trade-offs that are associated with adding EGR or hydrogen in order to obtain improved performance from the engine. In terms of emissions, you find that with use of natural gas, the carbon monoxide emissions are lower. Carbon dioxide emissions are typically lower because of the lower carbon content in the fuel. However, there's an increase in the amount of methane emissions, but this is primarily seen in engines which have conversions which are done by the end users themselves, and who are not completely aware of the need to tune the engine in order to reduce the emissions when you switch from gasoline to natural gas. So as I mentioned before, tuning the engine and getting the right spark timing and injection timing, if improperly done, can result in increase in emissions instead of decrease that you would expect by switching to natural gas. Finally, NOx emissions are higher, but then, as I mentioned before, you can do exhaust gas recirculation to reduce the amount of NOx. And at the same time, if you want to keep your flame speed high, you have to add hydrogen into the fuel in addition to doing EGR. I'm going to skip these graphs for now, and just kind of go over some of the major technology challenges and solutions that you come across when you're converting from gasoline to natural gas. You find that in terms of performance, there's lower volumetric efficiency, which can be fixed by either turbo or supercharging the engine, or by direct injection of fuel into the combustion chamber. You have a lower flame speed, which can be tackled by adding hydrogen to the natural gas in order to increase the flame speed of the mixture. And finally, you have, in terms of emissions, you have increased emissions of NOx, which can be fixed by addition of use of exhaust gas recirculation. And coupled with all of these, you still need proper engine tuning to get the optimal performance from the engine, as well as to reduce the emissions. I'd like to also go over briefly and talk about the use of natural gas in compression ignition engines. So compression ignition engines occupy a large market share in goods, vehicles, and diesel electric trains. And there's a sizable market share in Europe so there's a sizable use of diesel engines in passenger cars and buses in Europe. Compression ignition engines have inherently higher compression ratios, which means that they're more amenable to the use of natural gas, which has a high octane number. And finally, the major considerations for the use of natural gas in compression ignition engines are two things. One is fuel injection, and the second is fuel ignition. So if you consider fuel injection, you essentially run into the same sort of problems that you had with gasoline engines, in that the use of natural gas results in a drop in loss in volumetric efficiency. One of the good things about diesel engines is that there are no throttle valves, so the volumetric efficiency of diesel engines are naturally higher than those of gasoline engines, so that the net loss and net result of adding natural gas into diesel engines is that the volumetric efficiency only drops down by about 1 to 4%. And finally, there are other techniques to improve the volumetric efficiency, such as by varying the injection pressure, which I'll skip for now. In terms of ignition of natural gas, typically the way you have combustion in a diesel engine is by auto ignition of the fuel-air mixture. But one of the problems that you face when you switch over to natural gas is that the fuel mixture does not auto ignite at the typical compression ratios that you encounter in diesel engines. So in addition to having natural gas, you now need to inject some kind of a pilot fuel that will initiate the combustion process. So now, in addition to having natural gas, you typically inject about 30% of pilot fuel that allows you to have ignition of the mixture inside the engine. So typically, the natural gas fueled compression ignition engines are dual fuel. They have the natural gas and then the pilot fuel. And this pilot fuel tends to be diesel, because you need a fuel which has a high Cetane number and which can actually ignite the mixture. So we end up going back to diesel in some respect in order to achieve that ignition process. What the figure here shows is the energy release as a function of crank angle for two different cases. So the dark line is for the unmodified diesel engine, and the dotted line is for the modified dual fuel cycle. What you find in that in both cases, you have an initial peak because there's some amount of fuel-air mixture that ignites rapidly and releases energy, and followed by energy release from the rest of the combustion process. I think in the interest of time, I'm going to skip ahead here a little bit and talk about I'll just go through some of the major technology challenges and solutions with using natural gas in diesel engines. So one of the factors that you encounter in diesel engines, just like in gasoline engines, is that you have lower volumetric efficiency, and natural gas also, again, has lower flame speed. So the way you fix these problems is the same way that you try to fix them in gasoline engines. You try to achieve direct injection of fuel into the combustion chamber, and the lower flame speed you try to fix by using hydrogen, again, hydrogen addition into the fuel. There's, again, an increased amount of emission of unburned hydrocarbon and carbon monoxide in these diesel engines converted to run on natural gas, especially at low loads. And you, again, use exhaust gas recirculation to reduce these emissions. Now, one of the topics I want to briefly discuss is just the computational modeling work that people have carried out to simulate the thermodynamic cycle in internal combustion engines. And this is a very broad topic by itself, and there are entire books which are written upon this topic. But I just want to discuss some of the major aspects of the modeling work that is done with respect to internal combustion engines. So you find that there are numerical models of increasing complexity and levels of detail to simulate engine cycles. The major process that you need to that you're trying to model in these simulations is the air intake and transfer process, the mixing of fuel and air, the combustion process itself, and finally the exhaust transfer and emission process. The simplest analysis consists of what we saw in a few slides before, where you take just the cycle and do a first law thermodynamic analysis, and then you get some expression for thermodynamic efficiency and work power output from the engine. Then you can do a more detailed analysis where you actually include thermodynamic models or multidimensional fluid dynamic models in order to simulate the engine cycle. Now, the major objectives of doing this kind of computational work in engine modeling is, one, to develop a better understanding of the underlying physical process, to identify the key controlling parameters that influence engine performance and emissions, to be able to predict engine performance using these models, so that you can reduce the workload for the test operator who's basically getting the same data, but by running very expensive tests on these engines. You also want to be able to provide data to design engineers who can validate innovations in engines prior to their development, and also come up with improvements for improved performance from the engine. So the typical models that you see typical simulation approaches that you see in engine models are thermodynamic and fluid-based models. So thermodynamic-based models are the simpler kinds. They're basically based on the first law of thermodynamics. Their time is the only dependent parameter. They're zero-dimensional in space. And the solution basically involves ordinary differential equations. So these are sort of initial value problems where you have a certain boundary condition, and then you have a differential equation for each of the parameters that you're solving for, and it allows you to predict the thermodynamic state of the contents inside the cylinder during the course of the cycle. So you basically, what you do is you go through the different engine processes, such as intake, compression, combustion, expansion, and exhaust, and you put in data from models which for other things that feed into the cycle, such as the thermodynamic properties of the fuel-air mixture, the heat transfer from the gas to the wall, the combustion rate, emissions, etc. And you feed all this information into your zero-dimensional model, and it allows you to predict the power output and efficiency of the cycle. Now, in a more detailed models, which involves multidimensional fluid dynamics, you actually solve all the fundamental equations which involve the conservation of mass, momentum, reacting species, and energy. In this case, you have both space and time as independent parameters, and they're multidimensional. In this case, the solution involves partial differential equations, which are more difficult to solve and requires a large amount of computational resources. So what are the kinds of equations that you solve in these multidimensional simulations? You have conservation of mass, momentum, species, and energy. You make an assumption of an ideal gas equation of state. And apart from this, you also need other models, such as those for reaction, spray, turbulence. And it depends. The more models that you include, the more complicated your end simulation is going to get. But then it kind of depends on what you're trying to achieve with these sort of simulations and how complicated you want to make them. In terms of just looking at the combustion modeling, you can have a simple model that basically tells you that this is the amount of heat released during the cycle, and the combustion is modeled by a simple heat release model given in terms of something called a wave profile. So I can illustrate that in a graph over here. So you have on the y-axis, what I have plotted here is something called the mass burn fraction, and on the x-axis is the crank angle. So if you follow this curve, this blue curve, it goes from 0 to 1. So it means that when you're at 0, none of the fuel is burned. When you're at 1, all the fuel is burned. So you basically input a function such as this, which is obtained from empirical data into your to simulate the combustion part of the cycle. So as you follow this curve, the amount of mass fraction of fuel burned increases, and so the amount of energy released increases. And you can basically use functions of this kind to simulate the combustion process. And these are pretty widely used in engine simulations, and they give realistic results in a reasonable amount of time. Now, the more complicated way to do it is to actually include the full chemistry of the fuel-air mixture. So in this case, you have to include detailed chemistry by using a reaction mechanism for the fuel-air species, which includes all the reactions and all the species that can be formed during the combustion process of the fuel with oxygen. So in this case, there are many more equations which are added into the problem, because you have a lot of species and a lot of reactions. Even for a simple species like methane, for example, you have about 53 species and 325 reactions. And you compare that to gasoline, where you have thousands of species and even more thousands of reactions. And so this becomes extremely expensive to do computationally. So this just kind of points out that there are issues to be dealt with when you're trying to include detailed chemistry in your engine simulations. Now, there are several ways of reducing the computational requirement for these kind of simulations, and I won't go through them, but I'd just like to give you a flavor for the particular method that we used in our work for solving these sort of problems. So one of the things that we do is that we try to simplify the problem, first of all, as much as possible. So if we consider a problem, a reacting flow problem, where you have fluid dynamics coupled to some sort of chemistry, let's first of all throw out any turbulence out of the issue problem and just focus on a laminar flow regime. you also make an assumption that you're operating at in low Mach number space, which means that you're pretty much incompressible. And so this allows you to solve a set of simplified equations. In this particular regime, you would have an expression for mass conservation which looks something like this, and momentum conservation which looks something like this. Now you get back to the problem of how you solve, how do you include detailed chemistry without exceeding your computational resources. So the way that we do it is by using something called a flame-lit progress variable approach. Now, I definitely don't have enough time to go over the technique, but I'd just like to kind of give you a flavor for it. Basically, the way you carry this process out is that you know that if you are going from a completely unburned state of fuel to a completely burned state of fuel, you're essentially going through a whole series of different thermodynamic states. So what we do in this case is we make a table that captures all the different thermodynamic states that are possible when you're going from the unburned fuel-air mixture to the completely burned fuel-air mixture. And in the course of the fluid dynamic simulations, all you do is that you look up the properties from these tables depending upon certain parameters that are solved for in the simulation. So say you're at 50% state of reaction, then you look up in the table and you get all the thermodynamic properties such as density, viscosity, flame speed, temperature, etc. for the mixture, and then you plug that back into your numerical simulation. So it's sort of a lookup table procedure that you're tracking the state of your mixture by using just 2 parameters instead of using the entire chemistry. But all the entire chemistry is still captured because it's still there in your table that you have created prior to running the simulation. So just to give you a flavor for the sort of results that you can, this is sort of the one result that I have from my research in here, but it basically shows the formation and propagation of a flame front. So the red stuff in here is the burned stuff, the blue is the unburned mixture. You have a flame that generates and propagates into the mixture. And so this is a simulation that involves detailed chemistry with hundreds of species and thousands of reactions, but it is something that can be done on a single processor in an hour by using our lookup table procedure. And these sort of procedures have been used by other researchers to simulate complete engine problems. And here you see one of the results where the cylinder pressure trace predicted by simulation agrees pretty well with the computational predictions, with experimental results. And since you're using detailed chemistry, you can get results for pertaining to the emissions from these engines as well. And they match pretty well with the experimental data. So just to quickly summarize in the few minutes that I have, we've seen that one of the ways of reducing the reliance on foreign oil is by diversification of energy resources, by using natural gas, by adding natural gas to our portfolio of fuels that are used in transportation applications. The current resource in natural gas and future prospects make it a viable source of energy for transportation purposes. We have seen some of the advanced techniques of identifying and extracting natural gas. The natural gas vehicles have shown to be able to reduce the amount of emissions that engines be able to reduce emissions into the atmosphere as compared to conventional fuel vehicles. And also, we have seen some statistics that show that there's can be a rapid growth of natural gas vehicles in the immediate future. We've seen some of the aspects relating to the use of natural gas in spark ignition and compression ignition engines. I won't go over them, but there are several trade-offs that are involved in doing these conversions, and you have to keep note of them in order to obtain the best performance from the engine with the lowest amount of emissions. And finally, the implementation of natural gas is already in an advanced stage, but there is room for further development, and this can be aided by some of the computational tools that I tried to describe to you in the last part of the talk. So with that, I think I'll stop, and if you have any questions, I'll be happy to take them.
Do you have time for one or two questions?
You keep talking about injecting hydrogen.
Yeah.
And that sounds like a whole new set of elements
Yeah.
that go into the system to inject gaseous hydrogen.
Mm-hmm.
Is it gaseous hydrogen, or is there another way of doing it, or doesn't that make it much more complicated?
It does make it more complicated because now instead of just switching from one fuel to another, you're switching from 1 to 2 fuels. And then you have to consider the fact that you need to also carry hydrogen on board in order to be able to supply that to the engine. So it does make the problem more challenging. From what I've looked at in the literature, I find that improvements in performance can be achieved currently even without the use of hydrogen. Hydrogen gives you an additional bonus and improves upon the current performance. So I would say it's not an essential part, but it does add to the benefits that you can achieve by switching from conventional fuel to natural gas.
I have a question. How much computer time did it take to do your simulation there?
The one flame simulation that I showed you was done on a processor, which is basically a desktop processor, and it took about like an hour to do. There is some more time which is required because you first have to create a table that contains all your thermochemistry in it, and then you run your fluid dynamic simulation. But even those run pretty quickly.
Last question?
But just to follow up on that, I should emphasize that this is a much simpler problem than what you encounter in an engine. This is a simple laminar flame that's propagating in a mixture. In an engine, first of all, you have a turbulent environment in which you have many different time scales and length scales, and then you have a mixing process, all sorts of things going on at the same time. So it would definitely, even with these sort of models, it would still take a large amount of time in processing power to run an engine simulation. But just to give you a perspective, the most highly advanced code that the Department of Energy uses for simulating internal combustion engines, something called Kiva, K-I-V-A, takes about 30 hours to simulate one single cycle, just one rotation of the crankshaft, and that's not even with detailed chemistry. And so it's incredible the amount of resources that you can burn off.
Covered it. Maybe I missed it, but if you took a natural gas engine, how would it compare to the internal combustion engine based on gasoline today? You know, say one based on pretty high mileage and moderate performance, another one based on high performance and moderate mileage. Is it anywhere close, or just curious?
You mean like a hybrid engine, or
No, well, maybe a hybrid, but and just take gasoline, just a regular internal combustion. You know that. You know.
In terms of efficiency, I think a natural gas engine would compare favorably with even a modern gasoline engine, which might have, you know, advanced strategies like direct injection or stratified charge or variable valve timing and so on and so forth. I can't really say about the efficiency. I'm pretty sure the emissions are lower, but in terms of mileage and the overall efficiency of the engine, I'm not entirely sure how that compares.
Dr. Ben, thank you very much.
Thank you.
Great talk.
Thanks.